Here again, we have another modeling type exercise for nonmetal oxides, whether they behave as acid components, basic components, or neutral components. So I thought here, compare and contrast the carbon monoxide with carbon dioxide. Totally different compounds. So carbon monoxide, is it soluble in water? Yeah, it's a gas. So can it dissolve? Can it become aquated? Yes, it can. Can it fit into the tetrahedron traps? Yes. Is it actually polar? Yeah, we talked about this before. This guy's polar. So is he going to like water? Yeah, water's going to interact with this guy. Polar likes polar, right? So the solubility should be pretty significant here. So I'll put the arrows going a little bit in that direction. So that's my dissolution process. And then I stop. Because carbon monoxide is like permanent gases. If you remember what we were talking about previously, that's nitrogen, that's oxygen, that's argon. They're like that. They have low solubility depending how London dispersion reactions or if they have dipoles present, etc., etc. Well, that's non-polar, that's not polar. That's definitely non-polar. This guy's polar though. So this guy, you would expect the solubility to be a little bit higher. So let's go on to carbon dioxide, which has a totally different behavior. And it's related to, biochemically, the pH in our blood helps regulate it along with the phosphate system. So we got the carbonate system. So we have carbon dioxide, gas, can be aquated. This kind of reminds me of Henry's law too, and I think the chemies in the class can relate to that, and the biochems in the class. So Henry's law, solubility of gases, we assume they're ideal, and that we'd stop right there. But is carbon dioxide not an ideal gas? It's a real gas. So what happens is part of the dissolution process that I call dissolution, which is part of the overall solution process or solubility process, this guy can go on and react with water. So if I go and use my model, I just add the water molecule to this guy and see what I got. So I got H2CO3 aqueous. Wait a minute, I recognize that. That's carbonated water. That's a multi-billion-dollar operation a year. We pay a lot of money for carbonated water or our beverages. We like fizz. Okay, so carbonic acid. But is carbonic acid a strong acid? No, if you look at the Ka table that we got, Ka1 is 10 to the minus 7, and we won't worry about Ka2 because it's 3 orders of magnitude even smaller, so we'll just focus on Ka1. It's not very acidic. It's a weak acid. But it helps control our pH in our blood, etc., especially with the bicarbonate. It's conjugate base. So what can this guy? So that I call my dissolution process. My dissociation process based on the Ka, we can put some arrows on that guy. Dissociation. Almost lost my train of thought. So that means the carbonic acid can dissociate, not favorably, but the Ka shows me I get a little bit, so I expect the pH to be around 7 or lower. Get my hydrogen ion, aqueous, plus my bicarbonate. Which in another discussion is amphoteric. But that's to be continued on another slide or video. So this guy's a weak acid. Pretty important, and we'll stop there. Equilibrium arrows. So we would expect, I'll give us a little smidgen to that. To be able to say this here, that that's more favorable in that direction, I would have to do some thermodynamic calculations. In other words, I give you standard heats of enthalpies, entropies, let you calculate delta G, and you can calculate the equilibrium constant for this guy. We know this guy, we can actually calculate this guy too, which is pretty cool. Especially for the engineers in the class.